what I was telling you was we understood how we got to these equations, and there was a question on classification of vector fields. So I was telling you that, you know, based on whether they have curl, they do not have curl, they call it as, you call it as solenoidal or irrotational, divergence free and things like that. But at the moment we are concerned with electric and magnetic field. So at the moment we are going to see what is that electric and magnetic field which can simultaneously satisfy all these 4 Maxwell's equations, or we are trying to figure out a set of fields which can satisfy both all 4 of these Maxwell's equations. And so the objective is now, today's objective is to find an EH, the magnetic field that satisfies all 4 Maxwell's equations. Right, that's the objective. What's the nature of that E field and that H field? It satisfies all these equations. My original plan was to do a dielectric separately, but I think since we are running short of time, we will do a general case and then talk about dielectric as special cases. So what we want to do is to solve for these equations, 4 equations that we have written down, such that the E that we get satisfies all. So essentially I am trying to solve for E and H. And if you see, E and H are coupled. Curl of E is related to H and curl of H related to E. So you basically want to uncouple the equations. You want to uncouple the equations so that we are at a better position to solve. They are coupled because E is related to H and H is related to E. So I am going to uncouple that. So how do we uncouple that? So I have curl of E is minus mu del H by del T. I use again vector calculus to do this. The key is I know what is curl of H. I know curl of H through this. So I want to be able to substitute for curl of H in terms of E. So I want to get something like del by del T of curl of H here on the right side, so that I can substitute this in terms of E. By the way, my J is sigma E, which is my Ohm's law. So I can get everything in terms of E. But the moment I have curled the right hand side, it means that I have to curl the left hand side also, so that everything is balanced. Which is why we do this curl of E, so that I get, in fact I get minus mu curl of del H by del T, and this is space variation. Del is a space variation, this is a time variation. These are 2 operators which are operating independently. So I can pull out this, it does not matter whether I take a curl of del H by del T or I take a curl and then differentiate it. The order is immaterial. So I can write it this way, and the motivation of writing it this way is that so that I can substitute this curl of H as J, which is sigma E plus epsilon del E by del T. Remember we discussed about the constitutive parameters yesterday. So the constitutive parameters of the medium that I am talking about are mu, sigma, epsilon, where this epsilon is epsilon naught, relative permittivity of free space times permittivity of free space times relative permittivity. Mu is mu naught mu r, and sigma is the conductivity. This is the medium that I am talking about. Now the left hand side is this is from vector calculus. Del cross is del of del dot E minus del square E. This is a vector identity. And the right side is minus mu sigma, I pull sigma out, del E by del T, because sigma is not a time varying function, it is constant, minus mu epsilon del by del T of del E by del T. So, this is del square E by, so this is a second order differential equation now. The left hand side is telling me the variation of del. Remember, del is variation in x, it is a directional gradient, it is talking about del by del x ax cap plus del by del y ay cap plus del by del z az cap. This is the meaning of, this is what del. So, this is space variation and the right side is actually time variation. So, I am able to relate the space variation of E to the time variation of E. And remember, I have only E in my equation. I have uncoupled the equations. I have an equation only in terms of E now. The question is, so this is what is general for any medium. But now if I put in a condition and say that the medium in which this field is existing is charge free. If it is charge free medium, I do not have any charge in it. So, let it, so first assumption is what I am putting, it is a charge free medium, which means that my rho charge density is 0. So, because charge density is 0, my divergence of E is 0. There is no charge, there is no electric field, there is no divergence. So, it does not mean field itself is 0, field can exist, but its divergence is 0, it is not spreading out, that is what it means. Under that assumption, how would this equation look like? My divergence of E is 0, so I have a del square E equal to, all these negatives will get cancelled, mu sigma del E by del T plus mu epsilon del square E by del T square. This is my general wave equation for a medium which has a specific sigma, which has a specific mu, a specific sigma and a specific epsilon. This is your general, we call it as wave equation because ultimately the solution will turn out to be, it will turn out to be a wave because there is a space variation and the space variation is related to the time variation. It is not that I have some time variation, some oscillation independent of what is happening in space. So, there is an oscillation in time and there is a variation in space and both are related to each other through this equation. So, this is my general wave equation. Now, I am going to put one more condition here, one more constraint here is that the conductivity is 0. Let us say the conductivity is 0, which means no current, which means my J is 0. This is the second condition. We will relax this condition later if we get there, but if sigma is 0, my wave equation reads this way, mu epsilon del square E by del T square. So, this is the wave equation for a pure dielectric medium. What is the meaning of pure dielectric medium? It means there is no current. Conductivity is 0 for this medium if it is pure dielectric. It is a complete insulator, perfect insulator, there is absolutely no current in the medium. For that medium, this is what the wave equation reads as, this is how it reads as. this equation looks nice. Now the next objective is, what are the possible solutions for this equation? What are the possible solutions for this equation? Before we get to this, I will also tell you one more assumption which we have made, which I have not told explicitly. What we have assumed is that D is epsilon E, or we have assumed that it's an, well, at this moment we have not really made that assumption, but we are going to do that assumption that it is an isotropic medium. We will need this assumption for the simplest case. It is not that the wave equation does not hold good for an isotropic medium. This equation, this general equation is true for any kind of media, but I am going to make an assumption it is an isotropic medium. Now the question is, the natural question is, what is an isotropic medium? The answer to that is, if it is isotropic medium, your epsilon is a scalar. Now your epsilon is actually epsilon naught epsilon r. So which, if I say the medium is isotropic and I say epsilon is scalar, I actually mean epsilon r is a scalar, because I know that epsilon 0 is 8.85 into 10 power minus 12, that is already a scalar, that is a constant number. Epsilon r is also a constant and it is a scalar quantity. What does it mean by this? It means, physically what does it mean? It means that if I apply an electric field which is having components Ex Ax plus Ey Ay plus Ez Az, then so if E is the applied field, then my D is epsilon 0 epsilon r Ex Ax times Ey Ay plus Ez Az. So for example, in the case we considered yesterday, in the problem we considered yesterday, we considered water. Water had a refractive index of 1.5, so epsilon r was 1.5 square. So this is a constant number. D is directly proportional to E. In other words, if D is along this, if E is along this direction, D is going to be a vector which is something like this. They are in the same direction. That's what it means in an isotropic medium. How else can it be? What is the meaning of anisotropic medium? Now in anisotropic medium, without going to very detail, I can tell you what anisotropic medium is. In an anisotropic medium, what happens is, if my E is in a specific direction, my vector D can be in some other direction. If E is in a given direction, D need not be in the same direction. D can be in an arbitrary direction. In other words, I can tell that all materials in general are anisotropic. Isotropy is only a specific case where D is parallel to E. In general, D is not parallel to E. How do I represent this? I represent it by saying that dx, dy, dz, which are the three components of D vector, is not a linear multiple, it is not a scalar product, but it is a tensor product Ex, Ey, Ez, and there could be epsilon 11, 12, 13, 21, 22, 23, 31, 32, 33. This is in general, this is epsilon vector, well, I should call it as epsilon matrix of an anisotropic material. To give you an example, I could have epsilon matrix like this. I could have, let us say, E along using blue, E along the x direction alone. In this anisotropic case, my D could have some random orientation. Why? Because if E has only x component, it means dx is epsilon 1 Ex. My y component and z component are y component and z component turned out to be 0 because I said E is only along x direction. But dx is epsilon 1 Ex, epsilon 12 Ey is 0, 13 Ez is 0. That is fine. But it does not mean that dy dz's are 0 because dy is now epsilon 1 Ex, epsilon 21 Ex, epsilon 21 Ex, Ey and Ez could be 0, dz could be, dz is epsilon 31 Ex, which means if I apply an electric field in this x direction, the electric displacement, the flux density is appearing in 3 different directions, or rather it is a combination, or it could be in an arbitrary direction with 3 different components. So this is an isotropic material. I mean, you can go further and say that I can, so what is isotropy in this case? If my epsilon 1, 2, so if for an isotropic material, what would happen is, I would actually have epsilon 1 to all these cross products, whatever I am marking as green, they are all zeros for isotropic material, and I can say that epsilon 1 equal to epsilon 2 equal to epsilon 3 is the epsilon of the medium. This is followed, then it is isotropic, because in that case all these components are 0, only you have only the, if you have only the diagonal elements surviving, and if all those diagonal elements are equal to each other, that is the isotropic material, which is why I said isotropy is only a specific class of anisotropic material. The point we are making is, when all what we are solving for, when we are talking about possible solutions, we are considering only isotropic medium, which means we are not considering the case where dx, dy, dz are dependent, all 3 are dependent on Ex. In our assumption, dx is related to Ex. These relations are not there. It does not mean that Maxwell's equations is not true for an isotropic medium. Maxwell's equation is true for any kind of medium, but our discussion is limited to isotropic medium. So that is the third subtle assumption we are making. First assumption, we said it is a charge free medium. Second assumption, we are saying there is no current. Third assumption, we are making it is a isotropic medium. Under these conditions, we are asking ourselves the question, what are the possible solutions of the wave equation? It's not very easy to find the solution of this wave equation because it's a second order differential equation in time and space, and we don't have any boundary conditions as yet. For a second order differential equation, we need at least 2 boundary conditions to completely solve it. So what we are going to do is not to apply any boundary conditions. We are going to solve this equation initially. Throughout this course, we are talking about unbounded media. We can talk about bounded media probably in the next set of lectures, but in this set of lectures, we are talking about unbounded media. Okay, so that is the fourth assumption that we are talking about. We are searching for this solution in an unbounded medium. There are no boundaries. What we will use is a tool which is very powerful, where we say my E field is harmonic in time. We are going to be solving this for electric field that is harmonic in time. So, that is the fifth assumption we are doing, fifth condition. What is the meaning of harmonic in time? As a function of time, you see this E field varies as a function of time and as a function of space. The only thing we are doing is, we are saying the excitation field, the source, whatever that source is, that gives you a field that is oscillatory in nature. It has single frequency omega, angular frequency omega, like a simple pendulum. It is harmonic in time, it is repeating in time, and because it is harmonic in time, I can represent this E field as, remember this is a function vector, that is a function of position and a function of time. The E field has dependence on position and dependence on time. By saying it is harmonic, what we are saying is that this is a vector now, x, y, z, it is changing as a function of position. Yesterday we wrote down, I drew some examples of vectors which is changing as a function of position. But when I say harmonic, what it means is that the time variation is given this way. I will be able to write this vector as E, which is a function of only x, y, z, and the time dependence is contained here, e power j omega. I am representing, I am using a phasor representation. If you have done AC circuits, in electric circuits, you would have used phasors. When we calculated the impedance of, wanted to calculate the impedance of inductor or capacitor, when we are analyzing an AC circuit which has an inductance and capacitance, it was easier to use time harmonic case because we could use a phasor representation. The power of phasor is that the moment I put it as a phasor, all the second derivative will vanish. Second derivative in time, I can write it as a multiplier. I do not have to do a derivative. I will show you how. But that was a power. We have used it in electric circuit, same thing we are going to use here. The point to remember is, this is an exponent, and remember e power j theta has cos theta plus j sin theta. It has a real part and a complex part, and my electric field is not complex. It is actually a real number. I know that it is a real number. It is some volt per meter. It is not imaginary. So, I have to be careful while writing this. I should say this is the real part of my electric field, is a real part of the phasor, which means I am claiming that my E, x, y, z, t is actually E, the vector which is dependent on space, cos omega t in general. I could have an arbitrary phase plus phi if I want, but I will use this phasor representation simply because when I use this phasor representation, del by del t of vector E is actually del by del t of vector E, x, y, z, e power j omega t, which is, now e power j omega t, the derivative is j omega. So, this is j omega, and I will end up with the same number, which is vector E. So, del by del t of vector E turns out to be j omega E. Second derivative, which is what we need in our wave equation, del square by del t square is j omega times, one more derivative of del by del t of E. So, I can write this as j omega square E, which is minus omega square. This is the power of the phasors. Just because I use these phasors, my wave equation reduced to minus omega square. Of course, I had mu epsilon E. That second derivative in time vanished. It vanished and became a multiplier omega square. Do I lose anything by doing this? I gained a lot of things by doing this. My complicated looking equation, which was in space derivative in second order, time derivative in second order, I could reduce that to only a space derivative in second order. My time derivative in second order vanished. Question is, am I losing anything? Actually, I am not losing anything by doing this, because you can ask you can ask me this question that, are my actual electric field harmonic? Do I have a single frequency oscillating? And the answer is no, it is not harmonic. In general, it is not harmonic. If I take, for example, antenna which is radiating electric field, be an antenna, your wireless signals are transmitted at a carrier frequency of 2.5 gigahertz, but on that there is modulation. So it's not a single frequency that is going in, there is multiple frequencies going in. But the answer is, I can always represent any signal that is repeating in time, I can represent as its Fourier components. So if I can solve my problem for each of the Fourier components, which is what I will do here now, because each frequency I know what's the answer, I can take a linear combination and say that the response to the system is a linear combination of the response of each of these frequencies. So long as I have a linear system, superposition works, and so this concept of time harmonic works, which is why all through in all books you will find electromagnetics wave problem solved it for single frequency. It is not that all the signals around us are single frequencies. No, all the signals around us are probably containing multiple frequencies. But the point is, it's easier to find the response of the single frequency, sum it up and find the response of the system. So with that, I take a small break here to see if you have any questions. Do you have any questions? If you have any questions, please type in the question tab. Okay, I'll keep a watch on this question tab, and if there are questions, I will break. So we came to time harmonic case. So we are working with 5 assumptions. Okay, there was a question from VCAP. You said I will explain boundary conditions in different cases. So we will come there. We will reach there when we talk about. See, I just talked about the different types of media. So let's solve the wave equation for each type of media. Then we will come to the boundary. So that will get addressed before the end of tomorrow. So we will continue here. So okay, so we will continue, go back to our wave equation, and now see the question we are asking ourselves is, what is the simplest solution? I mean, there could be multiple set of electric fields which satisfy this wave equation. So I mean, I could have infinite number of solutions for this wave equation, because there are no boundaries specified. It's unbounded media. So we are asking ourselves a question, which is, what is the simplest solution? Now before we go to the simplest solution, let's realize that even though it's written as a single equation, what does this actually mean? It's a vector equation, which means, as I wrote down earlier, my E actually has 3 components, Ex, Ey and Ez. So this equation actually means the following: del square E by, well, it's not E, I want to write it as the components Ex by del x square plus del square, because del square is del square by del x square plus y square and z square. So del square Ex by del y square plus del square Ez by del z square equal to minus omega square mu epsilon E. I have written the Ex. the x component of this equation. This is the vector equation. What are the components of the vector equation? This is the x component. Similarly, I have the y component, del square Ey by del x square plus del square Ey by del y square plus del square Ey by del z square equal to minus omega square mu epsilon Ey, and del square Ez by del x square plus Ez by del y square. So this is telling you how the z component is varying as a function of space, omega epsilon Ez. So this is telling you how the x component is varying as a function of space. This is telling you how the y component is varying. This is telling you how the z component is varying as a function of space. All this is hidden in this equation. It is actually telling you three sets of equations, three equations, which means that my E has a component Ex Ax plus Ey Ay plus Ez Az, and it has a time variation e power j omega t, and each of this Ex, Ey, Ez are functions of x, y and z. It's complicated, isn't it? It's not very complicated. It just tells you that if I pick a point in space E, at that point the E vector has three components, some x component, some y component and some z component. When I go to the next spatial location, it's likely that my Ex is changing, Ey is changing, Ez is also changing, which means the vector can point in totally different direction. That's all what it says. And if I solve this first equation, it will tell me how Ex is changing as a function of space. How is the x component changing as a function of space? Similarly, y and z. That's all what it means. So given this, I am trying to ask myself the question, what is the simplest solution for this equation? So we are asking this question, what is the simplest solution for this E? It satisfies this equation. It satisfies this equation would mean that it satisfies actually this equation, which means that it satisfies for this medium, it is satisfying all the four Maxwell's equations. So if I find an E which is satisfying these equations, I have found an E which is satisfying all four Maxwell's equations. So we are going to do simplest solution by trial and error. Simplest solution for x, y and z, x component, y component and z component. I don't have a t because I have already assumed it is e power j omega t. The simplest solution, let me take that there is no variation at all. Let's say it's a constant field is E naught. Let's say this is equivalent to, so let this is equal to constant. What does it physically mean? It means that constant vector in some arbitrary e cap direction. So as a function of space, let's say the direction is this e cap direction is given by this direction of this blue arrow, and my assumption is that at every point it is the same. At every point in space it's the same. So the physical meaning of this solution, my trial solution, is this. There is no curl, there is no divergence, it's a constant, it's constant everywhere. This is not an impossible field. I can have a field like this, no problem about it. Question is, will it satisfy my equation? Will it be consistent with all my Maxwell's equations? So if this is a constant, then I am going to try the simplest solution. So this is the trial 1 I am making for simplest solution. It's a constant. I am going to substitute in del square E is equal to, what was my equation? Del square, I cannot keep writing all these three equations, so I am going to write the short form, which is the vector form, minus omega square mu epsilon E, and I want to check this trial solution. It's a constant, which means it's not dependent on x, y, z. So if I substitute this solution in the wave equation, it means that del square E is 0 because it has no variation. So, there is no del by del x, there is no del by del y, there is no del by del z, so there is no second derivative. So, my left hand side is going to be 0 and the right hand side is minus omega square mu epsilon, which is again my E is, I have just assumed that my E is E naught in the E cap direction. What does this mean? It means that I have omega square cannot be 0 because I am talking about time varying fields. So, omega is not equal to 0 because it is time varying. I have some variation. Mu is not equal to 0, epsilon is not equal to 0, which implies E naught is 0. Which means I cannot find a field like this. The magnitude of the field, this is not an acceptable solution. So, the magnitude of the field is 0. It is a moot point, right? It is a moot solution. I cannot think about a field where the solution of the field where field is 0. So, that is a redundant solution. So, this trial 1 is unsuccessful. So, the conclusion from here is electric field cannot be a constant in space while it is time varying, provided it satisfies the Maxwell's equation. It has to satisfy the Maxwell's equation, so it cannot be a constant in space. There has to be some space variation. So, there must be some space variation. I do not know what that variation is yet, but there is some space variation. It is varying with space. So, it is like saying that if I set up an electric field which is oscillating in time here, I cannot have the same electric field all through in space. It has to change. The field has to change as a function of space, right. So, my first trial that, let me take the simplest case where electric field is constant, that does not work out. So, let me do the second trial where I am assuming that the electric field has a space variation, okay, it is changing as a function of space. Again, remember, I am looking for the simple solutions, I am not looking for more general solutions or anything. So, what I am going to do is assume that let the field vary, or rather this is easier, let the field be constant in the direction perpendicular its direction, okay, not in the perpendicular to the direction is a plane. So, let the field be constant in the plane perpendicular to its direction. Electric field is pointing in this direction. Let us say electric field is pointing in this direction. Which is the plane that is perpendicular to this direction? Let us say this is x direction. The plane that is perpendicular is horizontal. I am saying that in this plane it is constant. In this plane it is constant. It means it is varying only along x direction. It is not varying along y or z. That is what I am assuming. So, I am assuming that electric field is, let us say, along the Ax component and it is Ex. It is varying only as a function of x. Remember, we said Ex could be a function of x, y or z. I am not taking all variations, I am taking only a variation along the x direction in its own direction. And I will pick up e power j omega t, its time variation. This is my electric field. I am going to assume this is my electric field. I am again, as I said, I am looking for a simplest solution. So, I am not saying that there is a y component or x component. I am saying electric field has only one component and it is varying only in that direction. It is not changing in all other directions. That is again the simplest possible solution one can think. So the question is this acceptable? Is this valid? So to find an answer to that, let's find the magnetic field. Let's find the magnetic field. There is no violation in this del square E. So if I substitute in the wave equation, there might not be any violation because there is a variation in space and I have a variation in time. So let's try and figure out what the magnetic field. And the way I find magnetic field is I have Ampere's law. I have Faraday's law. I will use Faraday's law because I know E, so I can find del cross E. It's minus mu del H by del T. And because it is time harmonic, I can replace by del T as j omega. So minus j omega mu H. This is my curl of E. So my H is minus 1 by j omega mu curl of E. This is my H. I know E, so I am going to substitute here omega mu. How do I find curl? It's a determinant along AX, AY, AZ. I have only variation along X direction. I don't have a variation in Y direction. I don't have a variation in Z direction. I have only X component, so this is EX. I don't have a Y component, I don't have a Z. So the answer to this is minus 1 by j omega mu. This determinant, if you see, AX component is 0, AY component is 0, AZ component is also 0. So this is 0, which implies magnetic field is 0. What if magnetic field is 0? Can magnetic field be 0 if I have a time varying electric field? Actually not. I cannot have magnetic field 0 because a time varying electric field is always associated with a magnetic field and a time varying magnetic field is always associated with an electric field. You will be violating Ampere's law and Faraday's law if you don't have this condition satisfied. Which means that, but I know that H cannot be 0 if E is time varying. E is time varying, I must have a non-zero H. So where is the anomaly? Where is the mistake? This trial 2 is wrong. This implies that this assumption that let the field be constant in a plane perpendicular is wrong, which means I can never have an electric field such that it is constant in a plane perpendicular to its direction. The electric field is in this direction. If it has to satisfy wave equation, if it has to satisfy Maxwell's equation, it can never be constant in this plane. If the electric field is pointing in this direction, it must have some variation in this plane. It can never be a constant in this plane. That's what it means. So if I want to sketch it, it means that if the electric field is in this direction, if E is along X direction, what does it mean by saying it's constant in the YZ plane? Any point in the YZ plane I pick, what is the electric field? It is constant. This was the assumption. At every point the E field, even at this point, the E field was this. This is the physical meaning of saying that the electric field is constant in the YZ plane. As a function of X, the electric field is changing. So as you pick another value of, let's say I pick another value of X, I have another value of, so this is another X value, that's another plane that I have drawn. Even in that plane, the electric field at this point need not be the electric field at this point. It could have changed because it's a function of X. So as X is changing, as the height is changing, the value of electric field could have changed, but in the same plane along Z axis or along Y axis, it is the same. So I can't have the field moving, changing only in its own direction. It has to have some variation along the y and z, which means the conclusion is that, because what happens is if I assume like this, magnetic field is coming out to be 0, which means that my E cannot be a constant in a direction, in a plane perpendicular to its direction. It has to change in a plane perpendicular to its direction. So that brings us to the third trial. Hopefully this trial will work, where I will say that E is, let's say, along the x direction itself. It has the x component, but just now I said it cannot be a function of only x. So I am going to assume it is a function of, I could assume y or I could assume z, does not matter, because it turned out that it has to have some variation along the yz plane. So I am going to assume it is a function of z. I could as well do this problem by assuming it is a function of y. E power j omega t is my variation in time. Now when I do this, what is my magnetic field? I want to make sure that the magnetic field is not 0. I want to make sure that the magnetic field exists. It is, I am going to use the same relation, minus 1 over j omega mu. What is the curl here now? The curl has changed, ax, ay, az. My del by del x is 0 now, del by del y is 0, I have a del by del z. Remember, this is the x component and this is the variation along z. So I have variation along the z direction. I have the x component, I don't have a y component, I don't have the z component. In this case, this is minus 1 by j omega mu. Ax component is 0, y component is minus ay times 0 minus del Ex by del Z, and Z component is 0, because this determinant is 0. This determinant is 0. What survives is the y component. So what you will have is, you have 3 negatives, so I will end up with minus j omega mu del Ex by del y, del Z times ay. This is fine. So I start with an electric field along x direction. The magnetic field is coming out to be along the y direction. This is the simplest acceptable solution. So I will stick with this simplest acceptable solution. What does this mean? It means that I have my x, y and z. Electric field is along the x direction is what I have assumed. This is giving me a magnetic field which is along the y direction. Of course, there is a minus ay, depending on what this result of this derivative is. I could have a plus or a minus, but in general let me say it is in the y direction. This is the direction of electric field. My magnetic field is in the orthogonal direction, y direction. As I said, depending on the sign of my del Ex by del Z, it could be in the minus ay direction or plus ay direction. Either way, it is in the same plane. Where is the variation? The field is varying along the z direction, because it is probably changing along the, I don't know the nature of variation. I still don't know what is the nature of variation in space, but I know that it is changing as a function of, and similarly the magnetic field is perpendicular here in the y direction, and it is also changing along the z direction. Now this is the simplest possible solution, and this simplest possible solution where the electric field, so here the assumption is E is a constant in the plane, it's varying only as a function of z. It's constant in the plane containing its direction. In this case, its direction is along the x direction, and I'm assuming that when I move along x, when I move along the x direction, the magnitude of E remains the same. So when my y and z changes, the magnitude changes, but as a function of x, the value of electric field here and the value of electric field here are identical. Same with in the y plane. So the simplest solution is the solution where E is a constant in a plane containing its direction, which is why this simplest solution is referred to as a plane wave solution. I still have to tell you why it's called a wave, but this is the reason why it's called plane wave solution. We will also talk about phase constant and the phase remaining constant in that plane, but this is one reason why it's called a plane wave solution. The next thing to do is to actually find the exact nature of variation. You know, is it decaying? Is it sinusoidal? Is it logarithmic? Exponential? I want to know what that solution is. So what we will do is we will go ahead with this trial solution. So trial solution 3 has worked for us, where I am saying my electric field is a function of x varying as a function of z e power j omega t and along the x direction. And what is my equation? My equation was, remember, del square E is minus omega square mu epsilon E, out of which I have only the x components surviving. There are no y and z components. So the variation is, and the variation is only along the z direction. So out of these 3 equations, I have only the equation for the x component because I don't have the y and z component. And even in these 3 terms, my variation is not along x and y, so I have only this term surviving. So I have my wave equation as del square Ex function of z by del z square is equal to, the right hand side of the equation was minus omega square mu epsilon Ex, which is a function of z. This is the wave equation that I need to solve, which satisfies the simplest trial solution. And the general solution for this is exponential. So if I substitute, for example, I'm going to make it little easier by saying that this, let me say this is equal to, I'm defining this as, instead of these, I'm going to define this as gamma square Ex function of z, where gamma square is defined as minus omega mu epsilon. This is my gamma square. In this case, my Ex, or del square Ex by del z square, is gamma square Ex, a function of z. Remember, these are scalar equations. I'm writing for the x component of the electric field. What are the solutions for this? I have to integrate and figure out what the solutions are. But I know very well from my differential calculus that the general solution for this is, I could have a constant E naught or Ex. I will use the same notation as in the notes. So this is E naught plus e power, well, E naught plus e power gamma z plus E naught minus e power minus gamma z, because when I substitute e power gamma z, that also satisfies this equation. If I substitute Ex as e power some constant a, e power gamma z, first differential will be giving me gamma, second differential will give me gamma square. So that satisfies. if I substitute it as a e power minus gamma z, first differential will give me minus gamma times the function, second differential will give me plus gamma square. So both plus and minus are solutions. So I am writing the general solution. So general solution is a linear combination of e power gamma z and e power minus gamma z. And the E naught plus and E naught minus are constants. They can be complex numbers. So in general, they are complex constants, which satisfies this equation. This is my general solution. So if I substitute, my E is E naught plus e power gamma z plus E naught minus e power minus gamma z e power j omega t, because both has to get multiplied by j omega t ax. This is my simplest solution for the electromagnetic wave. It satisfies the wave equation. At the moment, we still don't know whether it is a wave. We just know that it is the simplest solution. Now the question is, we need to bring in some physical understanding for this solution. What does it actually mean to write that, say that the solution is this complicated looking mathematical expression? So to understand the meaning, let's first figure out what is this gamma square. Gamma square is minus omega mu epsilon, which means gamma is square root of minus 1, which is j root omega mu. Well, I made a mistake here. This is omega square. So this has to be omega square here. So this is omega square. So this is j omega root mu epsilon. This is what gamma. So let me say, in general, let gamma be alpha plus j beta. In general, gamma is a constant complex number. It has a real part alpha and an imaginary part beta. And of course, in this case, it has only imaginary part. It doesn't have real part. But in general, let me say, I'll tell you why I'm using this, because later on when we talk about the case where you are talking about the case where sigma is not equal to 0, it will turn out that that gamma will actually be having a real part as well as imaginary part. So as I said, let me write a general form. Alpha gamma is alpha plus j beta. Then this equation actually becomes E is E naught plus e power gamma is j beta. So this is j times omega t. Let me write it as minus and plus. I'll tell you why it is minus and plus. Omega t minus beta z, and this is E naught minus e power j omega t plus gamma is plus beta z. I mean, as far as this solution is concerned, nothing is changed, but and this is in the ax direction. This is my e direction, e vector. Now let's try and see what does this mean. And remember, this is the real part of this. My e is actually the real part. It's not a complex number, it's a real part of this. So my e is actually e naught plus cos omega t minus beta z plus e naught minus cos omega t plus beta z times ax cap. This is my mean. Now we are trying to see the physical significance of what does this mean. Why do you call it as a wave? What does it actually mean by saying that E is this? So let's take only one term here. Let's take one term at a time. So the first term is E naught plus cos omega t minus beta z ax. So I am talking about an E vector which has only x component, which is varying along the z direction, and that variation is given by cos omega t minus beta z. So if I were to plot as a function of z, because it's varying along z direction, what is the E vector, and E is along the x direction, and I would also have, let's say this is my y direction. I am trying to plot this quantity to understand what it means. I am trying to plot it, but I am little confused here when I am trying to plot it because I have two variables z and t, and I have only an axis for z axis. So which means I will have to plot it for different instants of time. So let me say I have t equal to 0. I have this instant of time t equal to 0. T equal to 0, I am going to plot this. So at t equal to 0, what is actually happening to this vector? This vector is E naught plus t equal to 0 cos of minus beta z. Cos of minus beta z is cos beta z. It's a even function times ax. So I have to be plotting a function which is vector which is directed along x direction, varying along z direction as cos beta z. So at z equal to 0, what is happening? I have E naught plus cos z equal to 0, I have cos 0 which is 1. So it is having a magnitude E naught plus, let's say this is the length of the vector whose magnitude is E naught plus, and the direction is along the x axis. This is at z equal to 0, E is E naught plus. At z equal to a value given by such that beta z is equal to pi by 2, which means z is equal to pi by 2 beta. At that z, if it is pi by 2, cos reduces to 0, the vector reduces to 0. In between, the value of the vector is going from E naught plus to 0. This is what the vector is doing. At z equal to 0, at z equal to pi by 2 beta, it is reduced to 0. Similarly, at z is equal to minus pi, it reduced to, so let's say at this point z equal to pi by beta, it would reduce to minus 1, which means cos would reduce to minus 1. So my vector is reaching E naught minus E naught plus. And again, after one more cycle, quarter cycle, it will go to 0. So if I take the envelope of this E naught plus, that envelope is doing something. This envelope is tracing a cosine function, and it is coming back, it's repeating its phase after a spacing which is, it started with 0. So this corresponds to beta z equal to pi by 2. This would correspond to beta z is 3 pi by 2. This would correspond to beta z equal to 2 pi, which means after a spacing which corresponds to beta z, after a separation corresponding to beta z is equal to 2 pi, or after a z corresponding to 2 pi by beta, the phase is coming back to its original value. Started with a crest, the wave is repeating itself after a distance z by 2 pi by beta, and this separation is what we call as lambda, the wavelength, the spatial distance after which the wave properties repeat itself. That is lambda, and that is 2 pi by beta. And what is beta? Beta was the imaginary part of gamma. Beta was the imaginary part of gamma, and the imaginary part of gamma is, in this case, omega times mu epsilon. So beta is omega times root of mu epsilon in this case, which means lambda is 2 pi by omega mu epsilon. So this was what was happening as a function of space at t equal to 0. Now what happens as time progresses? What happens as time progresses? Now if I want to see what happens as when time progresses, it's like saying, so what we saw here at t equal to 0 means it's as if I have taken a snapshot, I have taken a photograph of the wave, I have frozen the scene, and this is how my electric field vector is looking like. Now if I want to look at time evolution, I have to do a movie, but I have to do that movie at a specific location because I can't move time as well as space. It will be difficult for me to analyze. So let's analyze as a function of, if you want to do variation in time, let's assume space is fixed, let's say at z equal to 0. The same is true for other values of z. And what happens when z equal to 0? Your E vector is E naught plus cos omega t dx because my beta z is 0. And what happens to this vector? It is again a cosine function. So if I just keep plotting the same, I am looking at z equal to 0. So this was at t equal to 0. What is happening to this vector as time progresses? When omega t becomes a value such that it is equal to pi by 2, the vector which was having its peak here will get its null here. It's getting its null at z equal to 0, which means if I am tracking this vector, the vector would have actually had, so it had this magnitude, maybe it's at some other time between omega t equal to 0 and omega t equal to pi by 2, it got this magnitude and then it got a further smaller magnitude and then now it is, and as time progresses what happens, I am trying to do a time trace here. So as time progresses, so this is my z axis, this is my x axis, y x, it starts oscillating in the negative direction, then it goes higher, goes to the negative maximum, and then further on it becomes lower, it goes back, which means if I try to draw it in the same axis, in the same thing, I have this blue vector oscillating up and down, right? I would have it, so if I do the time trace here, initially the blue vector was here, then the blue vector would reduce. This is as a function of time I am plotting at z equal to 0. So in this location, if I am standing at this location corresponding to z equal to 0 and I am looking at the electric field, it's doing the same kind of sinusoidal oscillation, which means as the field is oscillating in time, it's also moving in space. That is where we get this idea of propagation, because when this, so let's take an instant where initially at t equal to 0 my field is this, and so my field reduced this way and it is doing this oscillation. At some other t, what would have happened if I had taken a snapshot was that this would have been a minimum, this position would have been a maximum, this position would have been a minimum, this position would have been the negative maximum, this position would have been a minimum, and so on. Which means the wave which was sitting here appears as if it is moving in this direction. And this happened because you have the specific nature omega t minus beta z. It's moving in this specific direction. So this means the first term here is actually representing a forward propagating wave. It will represent a forward propagating wave because as a function of time, if you keep looking at this, if you keep looking at the position of the crest, that crest is moving in the forward direction. And hence this omega t minus beta z is representing a forward propagating wave, which is why I have notation, I have looked at its amplitude as, put its amplitude as E naught plus. Now if you do the analysis same way for this wave, it will appear as if this wave is actually moving in the negative direction. So in general, my E field is the sum of a forward propagating wave. This is where the concept of wave is coming from, because as and when there is a time variation, there is a corresponding space variation. So there is a forward propagating wave and there is a reverse propagating wave, or wave propagating in the negative z direction. So the general solution is a plane wave, which we realized this is the equation for the plane wave, and it's a combination of a forward wave and a backward wave. The next thing to do is to figure out what is H. E is a wave. Is question we are asking is H also a wave? Now if my E we said is Ex a function of Ax, my H we figured it was Hy a function of Ay, because we just wrote down the matrix, the determinant, and figured that H has only the y component. And what is the y component? It is minus 1 by j omega mu del Ex by del z. So my H is minus 1 by j omega mu del Ex by del z, but in the Ay direction. Now let's calculate what this is. Minus 1 by j omega mu. What is my Ex? It is E naught plus e power j omega t minus beta z, and I need to take a differential of this. So this is minus j beta in the numerator plus E naught minus, I took a minus j beta, so I will have a minus here, e power j omega t plus beta z. I have already taken the beta outside. So this result is beta by omega mu times E naught plus e power j omega t minus beta z plus E naught minus, minus E naught minus e power j omega t minus beta z in the Ay direction. If you look at what this is, beta is omega times mu epsilon. So beta by omega mu is omega times mu epsilon divided by omega mu. So this is nothing but square root of epsilon by, we were deriving. So I said Hy we derived as beta by omega mu times E naught plus e power j omega t minus beta z, and there was a minus E naught minus e power j omega t plus beta z, and the point to note is that it is in the Ay direction, and what we just figured is that beta by omega mu is, beta was omega root mu epsilon by omega mu, so this is under root epsilon by mu, which means I can write this as E naught plus divided by eta e power j omega t minus beta z minus E naught minus e power j omega t plus beta z over eta. This factor omega mu by beta is what I am calling it as eta. Okay, it's a fixed ratio which is decided by the properties of the medium, and this is being this eta being real here, it means that E naught plus, and so this is my H naught plus and this is my H naught minus. Remember we are writing for H which means that this is the Hy is Y component, the total H field is this, which means your E field and H field are related. If you know the E field, I can write down what the H field is. Not surprising, but what is interesting to see is that it is different from the E field only through this ratio eta, which gets called as the E by H ratio. E by H ratio is called as eta. So this is the E naught plus ratio by H naught plus, if I can call this as for the forward propagating wave. Now if I take E, its unit is volt per meter, H unit is ampere per meter. So E by H is of the unit impedance. So you call this number as intrinsic impedance of the medium. Intrinsic impedance of the medium. Now the intrinsic impedance is real quantity, which means that E and H are in phase. What does that mean? If this was a complex number, then I should have written this as magnitude of eta times e power j some theta, and that would have appeared here, which means that my E and H are out of phase. But in this particular case, eta turns out to be real, so my E and H are in phase. But if I want to visualize this field, it is like this. I have, as a function of z, I have E along the x direction, I have E along the x direction, H along the y direction. So this is my x direction, this is my y direction, and along the z direction the field is changing. So I have a sinusoidal variation. Sorry, I have this kind of variation of the E field, and as E is oscillating in space and propagating in space, what is H doing? It is in phase, which means when E is at its maximum, H is also at its maximum along the y direction. Remember, I am just looking at the forward propagating wave, and it is along the positive AY direction, and E reduced its value, H also will reduce its value, this also will reduce, this will become 0, E goes to negative x, H will go to negative y. So H will do this kind of oscillation. So if I were to trace the H field, it's something like this. You have a nicer picture in the notes that I have given you, but this is how the H field is doing. The E is oscillating along x direction, H is oscillating along the y direction, and the wave is propagating along the z direction. So your E, H and the propagation direction of the wave, propagation direction is along the z, they are orthogonal to each other. And such a wave is called as a transverse electromagnetic wave. In a transverse electromagnetic wave, your E, H and the direction of propagation are orthogonal to each other. So a TEM plane wave is the simplest solution of Maxwell's equation, of the wave equation. So with that I complete today's class. I open the session for questions, and I also want to know whether we missed half an hour, so we will not be able to complete whatever we promised earlier. So I would probably, you should give a feedback to the QEEE team whether you want a extra session to complete and to discuss the tutorial problems if you are interested. If many of you are interested, we can organize an extra session. Otherwise, we will complete whatever we can in tomorrow's session. So I'll open the session to questions. One question I have here is, how is air treated as a dielectric? Okay. So the reason why air is the reason what happens in air is, or what happens in a dielectric is, when you apply an electric field, there are dipoles created in the system which will separate the charges, and when the field is oscillating, the dipoles are actually oscillating, and an oscillating dipole is a source of radiation, and that is how the field is propagated. So air is treated as a dielectric because it is this way that field propagates in air, and we will also see that sigma of air is close to 0. So tomorrow we are talking about when do you call a material as a dielectric and when do you call a material as a conductor. So there again we will realize that sigma is 0, so you will treat air as a dielectric. Are there any other questions?